Welcome back to my channel. I'm Brian Kathke, and in this video, we're going to be talking about the Data Lakehouse, and this will be an introduction to give you a conceptual background to what that is. Before I jump in, please consider supporting me on Patreon. You get direct access to me, special content, and periodic Q&As among the benefits. Now, one of the differences on my channel I try to maintain is introducing everything conceptually and making sure you have a firm foundation under which to understand the technical details that are discussed further on. And in that same kind of mentality, I'll be talking about the Data Lakehouse. So we'll be talking about Data Lakehouse to Data Swamp, revisiting the traditional data warehouse, what's so hard about that, and introducing the Data Lakehouse. We're going on a Wayback Machine, maybe 12 years ago. There's a lot of hype around Hadoop and the idea that you could do all kinds of massive data processing using Hadoop MapReduce, and as part of that, the Hadoop distributed file system. This sounded great. People said, let's use this stuff. So we got people out there and they threw stuff out into the data lake, which is really just a storage system, just like a file folder, right? Throw some files out there, did querying. Then they told their friends and they threw files out there and more people and so on and so on. And eventually you had lots and lots of data sitting out on these file folders with no data governance, no really thought about how it should be used. And this was called freedom, right? Hey, it was like, we don't need no education. We don't need no rules. Problem. Eventually they started asking questions like, what is this data? It was put out a year ago and the guy left. What happened? What is this? Is it current? Is it accurate? Where did it come from? Why are there so many bogus values in the data? How do I get the information I need? And has someone already gotten this data I need together so I can just use it? So this became a data swamp instead of a data lake. In other words, it became pretty useless pretty quickly. People started to, enter the trough of despair. This promise wasn't all it was cracked up to be. But in fairness, sometimes people just jump too quickly and they forget that the data warehouses in the SQL Server world also had to evolve. And you can't just throw away the core requirements. It's not, things don't work like that. There's no magic. But people forget that. And everybody sung the praises of the end of the old relational databases and all the requirements of doing a data warehouse. So let's talk about that for a minute. Let's talk about relational databases and the kinds of features that they offer to do a data warehouse. Well, we know that they support the structured query language and that they're built upon set theory. And EF-COD came all about all these roles, and they came up with this idea of a relational database system. And structured query language is a very rich and robust language that has been extended over the years. And the idea behind a relational database is that you have these objects to store data called tables. Each table is supposed to store a discrete set of information, maybe about sales or customers or products, and only about that information. So it relates all to that subject. You may have a relationship between given tables. Sales, for instance, has a customer. Somebody bought the product. So there's a relationship between these. Relational databases are also good at supporting transactions, right? What are transactions, Brian? This is how you maintain the data. It starts by inserting data. Then you need to go back and do updates. And maybe eventually you realize like the customer isn't going to be a customer anymore. You delete them. So insert, update, and delete are the kinds of things we do against our tables to maintain the data. And we do that in something called transactions. Transactions on a relational database support ACID, which means atomicity, consistency, isolation, and durability. You don't need to worry about all the details of what that means, but the idea behind it is sort of an all or nothing concept in which we apply all the related sets of maintenance tasks together, or we do them not at all. So if we consider something like the customer and sales, we have something called referential integrity here we want. In other words, we don't want to allow someone to insert a sales row unless there's a related customer, which is represented on the sales row, the customer key. That means that we have to first insert the customer, then we can insert the sales row. And if we can't do both, we should roll everything back. And that's the idea. So there could be more tables involved. We could have many tables involved, and we would wrap the whole thing up in what's called a transaction. Do this insert, do this update, whatever it is we need to do. And we put it together as a package called a transaction. And at the end of it, we say commit it. Now, if the commit has a problem, suddenly it runs out of space or something goes on, it can't do it, then it's supposed to roll back, or the programmer can test it and say, oh, something went wrong. I need to roll back the transaction, meaning undo everything as if I never touched it. Now, you can imagine you've done a lot of changes. It's important that you get rid of everything you did and return it to the state where it was before you even started. That gives it a sort of consistency. You may be missing data for that transaction, but at least you're not half baked. Some of it got through, some of it didn't, and you don't even know what got through and what didn't. So it's better to have this consistency. And that's supported in these transactions, all or nothing. It can do this or it doesn't do this. Another thing that extends the sort of integrity of the data are constraints. And there's a whole bunch of different types of constraints. You can see in the database picture there, we talked about referential integrity. And that means you can define a rule in the database that says you cannot insert a sales row unless the customer key is found on the customer table. In other words, if I'm inserting a sales for customer A, then customer A must exist on the customer table. There's a lot of other types of constraints. Domain constraints enforce that data types are what they should be, integers and decimals. You can't put the wrong type of data in a column. We have key constraints. What's a key constraint? Well, things like uniqueness. If you're going to have a key for a table, which is the unique identifier for a given customer, it has to be unique. So that's a unique key constraint. Entity integrity constraints mean that a key, a primary key, for instance, for the customer cannot be null. You cannot have null primary keys. We already talked about referential integrity constraints, and then we talk about column value constraints, also known as check constraints. So what are those, Brian? But the idea is that you can say sales cannot be, for instance, less than 0. In fact, probably should always be greater than 0. A date on a sale must be filled in. You can't have a null value. So null check constraints are one. You could say values are a certain thing. There's all these types of things that are meant to kind of keep a sane set of values in the tables. Supporting this whole idea of transactions are transaction logs. These are external files that are maintained when the transactions are occurring. So as you do inserts, there's this little transcription taking place in the database to say, oh, I see you're adding a customer. I see you're adding a sale. I see you're doing this and making these changes. And it's keeping track of all these changes so that when you say, oh, wait, something went wrong, it can use the transaction log to reverse the data back to the way it was before you started. When you say commit, it locks it down and says, okay, that's the way the data is, and the transaction log will record that that's the current state of data. This was committed. So transaction logs are really important for recoverability, and they also allow us to know what happened to the data. Typically in relational databases now, this is a self-contained world, right? The environment of relational databases that you can only go through the database server, whether it's Oracle or SQL Server software, to do anything. These are not external files like in a data lake. These are all self-contained in the database, and it must manage them. Periodically, to make sure we don't lose our data, if something goes wrong and the server crashes or something, DBAs will take database backups. And typically this is like nightly. We'll do a nightly database backup. And then during the day, all the transactions happening will be logged in the transaction log. So lo and behold, something happens and the system crashes and we lost all the data. Well, you would go and grab the backup, last backup, and it might be from last night, 8 p.m. And then you take the transaction logs of everything that happened since then to the latest transaction, and you apply those transactions for it. So you restore the backup and start applying the transactions until you get to the most current state you can get to, which hopefully is pretty good and you haven't lost much data. These are all parts of resilience and recoverability that SQL Server databases have been doing for a long time. Now, relational databases also include a lot of security because, again, you have to go through this sort of veneer wrapper around it to get at the data. So it's going to say, who are you? And do you have a password? And what permissions do you have in the database? So they have a lot of security around them. And they typically also support triggers. Additionally to triggers, there can be stored procedures and functions, which I'm not really going to get too much into because it's not critical to a database to have that, but it is a nice feature. You can store essentially programs in the database written in the SQL language. But triggers get back to sort of this data maintenance kind of thing. For instance, way back in the old days, triggers would be used to enforce referential integrity. Somebody would try to insert a row into the sales table, and you would have a trigger. And a trigger is something you write a piece of code that should execute when an action is performed on a table. So you try to insert into sales, and you say, well, if there's an insert on the sales table, before you do that, check that customer key coming in. Is it on the customer table? Yes, okay, let it go through. No, don't let this transaction happen. Don't let them do the insert. And there's on updates and on inserts and after and all these different types of controls around the trigger. I'm not a huge fan of triggers. I haven't used them in a long time, but there are use cases where they make sense. They can also be used sometimes to do automatic logging. You insert into the sales table and you could write to a log saying somebody inserted a row. Now, before we get into the data lakehouse and what it is, I need to talk about the two primary types of workloads that relational databases support. On the left, we talk about the transactional or online transactional processing, OLTP database workload. And on the right, we're going to talk about the data warehouse, which is probably what we're going to focus on, right? But we've got these two potential types of workloads, and both of these coexist and have coexisted in the relational database world for decades. But the bread and butter of relational databases really has been on the left, the transactional processing systems. These are databases that store your mission critical data. In other words, you've got your applications running and they're storing the database typically in a relational database. This could be your sales system, financial record systems like accounting and general ledger and accounts payable, banking transactions, all kinds of things that are absolutely essential for the daily operations of your business. Data warehouse purpose is reporting and it's decision making and planning. That's what it's kind of involved around. What should we be doing? What products should we sell? How can we do a better job? Transactional systems are focusing primarily on the data maintenance and doing it really well. So that's why you saw that thing about transactions earlier. Insert, update, and deletes. Key. They have to be fast, they have to be efficient, and they have to avoid a lot of locking because many different people could be trying to do these kinds of operations in different places all over the system. And nowadays, it could be a website that's distributed all over the world. People are trying to do updates and inserts. So it's an important thing. But remember, these are sort of small sets of data. It's inserting a sales row and a customer row and things like that, not hundreds of thousands of rows from a given single person. Data warehouse, it's not about maintaining the data. Typically, there's some sort of a batch window. Maybe once a night, ETL kicks off and it does all the loading and merging and freshening up the data to where it needs to be. What's really important is when people run queries, do Power BI, do reporting, they get quick responses in the querying, which is involved in sorting and aggregating, not looking at individual rows. So again, a very different focus here. In transactional systems, the thing that is really crucial, because these are like, if this is down, your business is dying and you have to solve this problem quickly. So it's crucial. It needs to be reliable. It needs to be secure. It needs to be resilient and very fault tolerant. You'll see lots of architectures where something fails over. The database system fails and it triggers a failover to a whole nother database system. And that may even have another failover. So if that goes down, it goes to a third. So a lot of things going on. It has to be recoverable. We saw the whole backup recovery thing where we can restore the database. If you lose it, you're in deep trouble. Whereas on the data warehouse, we're doing queries, we're doing lots of aggregation. Also, the originating source of data is the transactional systems, which typically the data from there is going to be pulled out and put into our data warehouses. So the transactional systems are really our system of record. They're the ones that are going to ultimately say what's right and what isn't. So they have to be accurate. The data warehouse has to make sure they pull all that into the data warehouse and get it right. Also means that data warehouses have a lot of integration. They pull data from many different sources and consolidate it so it can be used for reporting. And again, as I mentioned, aggregation of large data sets. And finally, transactional OLTPs databases use a modeling technique called entity relationship modeling, and they apply the laws of normalization. Remember that in your interview. So these ERM models allow you to eliminate data redundancy, which is the enemy of transactional databases. However, the data warehouse says, no way, you want redundancy. We're going to use dimensional modeling. We don't care if we have 50 copies of the same customer. All we care about is that the queries run fast. So a very different orientation. Now, why do I care about this, Brian? Why is this so important? Because when I talk about borrowing concepts and features that are in relational databases, I want you to remember that the data lakehouse is focused on emulating the data warehouse functionality. In fact, the data lakehouse name comes from taking data lake, data warehouse, and merging those words together to get data lakehouse. Very clever. All this is good, Brian. But what's the big deal? Why is it so hard to just add those kinds of features to a data lake? Seems pretty easy, right? Think about it for a minute. And this is important because as you run into trying to build your own data lake houses and things, you might say, why is this so challenging and how can I get around it? I'll tell you why. Because in the old relational database world, you got a single box. Everything's local, very simple. So you try to insert a row and you say, is that a unique row? It can very quickly check against the table and say, yep, that's unique. Doesn't exist yet. or whatever. That's unique row. This key doesn't exist. Referential integrity, not a problem. I go to insert a sale row, takes the customer key, says, is that on the customer table? It's all very local, very close, no network traffic really. It's all right there. Very efficient, all on one machine, simple architecture. Now, when you look at a scaled out data platform, whether it's Databricks or Snowflake or Synapse, it's a very different world. You've got many different nodes running, many different machines. They're actually separate. They can even be separated by some network barriers. This is a lot of overhead, and this could be like 10,000 nodes in a cluster. And bear in mind, these are actually files, right? It's not like the relational database world in which everything's wrapped in a single monolithic interface and a service that wraps it all up. These are actually separate storage files. In the Data Lakehouse, it based it on Parquet, which it enhanced and called Delta format, but they're just flat files. So this adds a lot of complexity because you say, okay, is this a unique key value? It's going to have to look at all the cluster nodes to find that out. If you said, is this customer key on the customer table? It's going to have to do a shuffle to co-locate the data so it can find out if that customer key is there or not. These are very expensive operations, and it's not an efficient use of a scaled out platform, but we need that functionality. So we're kind of in a quandary. And as mentioned, that the database is external files. So even though we're trying to emulate this sort of relational database functionality, it has some key differences, and that's a big one. It's just a bunch of files, really. Somebody could just take a file and delete it, and that's part of your database. So let's step back and let's say, how well has the Data Lakehouse implemented that old relational database data warehouse functionality? Like, where are they at based on our previous diagram? Well, Spark has had at least the query level select type of support for SQL since 1.0. It's been had that for a while, and it can do that on top of flat files. In fact, that whole data lake thing I talked about earlier, I should have mentioned, basically that was schema on read. You throw a file out there, define an SQL schema over it, which we call Hive, and then you can use SQL to query and all that stuff. And that's been around a long time. Bear in mind that Data Lakehouse wasn't worried about maintaining data. It was just querying data that was dumped out there. Now we're talking about maintaining it, and the good starting point is we have the SQL language to start with. Transactions have been implemented. This is huge. This is massive. And this is when people started talking about Delta Lake. What is Delta Lake? The beginning of Delta Lake was the addition of transactional support on a data lake. All right. It's based on Parquet, new format called Delta. But what does Delta really do? It adds transaction logs we're going to talk about in a minute. We get ACID support, right? So we're getting that kind of robustness. We can do a complete commit or rollback. Something that didn't exist only a few years ago now exists. And we have transaction logging. So a Delta file is really just a Parquet file, but it's got transaction logging. And we'll see more of that in future videos. Constraints. First time I'm not using green, I'm using an orange because although Databricks has done a great job of implementing many types of constraints on the Lakehouse, it's still evolving. There's still parts that aren't completely there. I used a primary key generator the other day using something called the identity column. Worked great, but then I found I had to kind of do a hack to get what the identity column value was so I could use it as a foreign key in another table, which is a very common thing. So I found it wasn't completely there in terms of its implementation, but I was able to get it to work, so it did what I needed. So just be aware it's evolving, and don't expect it to be just like your good old Oracle or SQL Server yet. The referential integrity constraints I'm really excited about because I honestly didn't think I'd see this in a scaled out platform, but Databricks says they got it there. I have not tried it yet, and it's in public preview, which means it's pretty far along. So take a look at that if you get a chance. I'm going to be interested in looking at that. That's a challenging thing to do on a scaled out platform. Now, security, honestly, you're in a cloud platform with Databricks. You've got to deal with that cloud platform's way of securing things, and bear in mind, this is not like a relational database that it's all wrapped around in the service. These are just files that are sitting out on Blob or Azure Data Lake storage or AWS storage or Google storage. So security, there's some grant revoke type stuff you can do within the data lake. There's some grant revoke kind of things you can do within the Data Lakehouse. But really, you need to really look at the cloud architecture you're working on and secure everything along those lines. So I wouldn't worry much about that. And as far as triggers go, I don't think they're implemented. I haven't really researched it yet. Last I checked, they weren't, but I'm okay without triggers too because they typically have caused more problems than they solve. So I typically avoid them, but I did want to mention them. Knowing Databricks, I wouldn't be surprised if they do implement them for those people that really want it. Database backups. Again, this gets back to you kind of had to do database backups when you're in this monolithic, specialized proprietary service called SQL Server or Oracle. Why, Brian? It's still storing files under the covers, but it doesn't tell you where they are, and it doesn't let you manage them or copy them. In fact, if you tried to do anything to them, you'd probably corrupt your entire database. So you need to leave them alone and let the system manage them. Because that's the case, you need to use the special extraction program called the database backup to write a database backup file. And then you have to use the database backup restore command to bring it back. That's not the case with something like a data lakehouse. These are flat files and you can do and slice and dice whatever you want. And it's up to you to really manage them and be careful with what you do. I'm sure that some functionality around governance for those is definitely needed. But the database backup idea probably is less relevant here. High availability and all those things and recoverability definitely are, and you're going to need to think about that. And definitely for these files that you're putting out on your lakehouse, figure out how you can make sure you have good recoverability, copies of them. Maybe you copy them to a few places in storage or move them to archive storage so that if something happens and you lose them, you can get them back. Typically, cloud storage does a couple of copies, maybe more, depending on the type of storage. But I think you should make sure you have the kind of reliability to make sure you don't lose data. What is schema evolution is first. In the old data warehousing world, I've seen many times where you're going along and somebody just throws a new column into a data set or a table that you're pulling, and you aren't expecting it. Happens all the time. Now, in the traditional world, everything breaks and you're kind of left around panicking, trying to solve the problem because nobody told you they were adding new tables or columns or making changes or dropping columns. But Databricks added a really interesting feature called schema evolution. In schema evolution, when new columns come in or changes occur, you can make a decision in your code and architecture to say, how do you want to handle that? And if you choose to, you can allow your schema to evolve, like adding new columns. So that's a very cool feature. And I'm sure you have to be careful how you use it, but good to have, because in this fast changing world with data lakes and all kinds of things being dumped into your data storage, you probably can't afford to just stop everything and do a project to figure out how to handle a new column. I want to add a few things to what I've said. I took a very specific viewpoint. It is based on my own background. If I look at the history of things, I come from that SQL relational background, and most people that are moving to the data lake do as well. And Databricks is aware of this. However, it's important to understand that the data lake ain't your old-fashioned legacy data warehouse. There's a lot of functionality in there that wasn't in the old world data warehouse. For instance, if we go to the right and look at Data Lakehouse, we get now, because of this new Data Lakehouse functionality, metadata and governance. So that's what the Data Lakehouse brings to us. But we also are getting all kinds of support for different types of file structures, the big data world, right? Not just structured data that we're used to, but pictures and images and sound and video and on and on. We need to be able to process that. It's not an option anymore. We need to be able to analyze videos and say what's happening in the video or transcribe it. We need to look at sound. We need to be able to handle all kinds of data. So this is something you just can't do in the relational database world. And we want to be able to support machine learning and AI, right? This is a big part of where things are going. Again, something that isn't traditionally supported in a data warehouse world. Now, I also want to call your attention to the fact that this is Databricks' view of their evolution, right? Going from your traditional data warehouse to the data lake, and then realizing they lacked the governance and features needed to be a proper data warehouse with all that transactional support. So we get to the data lakehouse. So this is theirs. There's a lot of other things they talk about. And if you look at this link at the bottom here, it says more. That's a link that will take you to a Databricks blog from about 2 years ago where they talk about Data Lakehouse and what it does and all these features. And it doesn't really take it from the sort of viewpoint I'm taking it. They're just looking at more from an overall functionality that was lacking that they're trying to build into the Lakehouse. So there's more in that than I've discussed here, but I hope this gives you a sort of smattering of what's involved and what the Lakehouse is about. And by the way, a link to these slides is available in the video description. So we started out by talking about the data lake to data swamp and the idea that, wow, we can handle big data, and everybody jumped on board and got so excited that they thought that the magic of this technology meant we didn't have to do any work anymore, just throw it out there and analyze. And that disillusionment was identified pretty quickly. Then we got to looking at, as Databricks did, what the traditional data warehouse did and how do we get some of that functionality back that we need in the data lake world. And then we talked about the architectural differences between a relational database and a data lake, which make applying some of these things particularly challenging, but somehow they did most of it and they're doing more. And so we talked about introducing the data lakehouse and all the things that have been implemented towards giving us that kind of data warehouse functionality. That's it. I want to thank you for watching. Please like, share, subscribe, put comments in and questions. And until next time, I'm pulling for it. We're all in this together. Thank you.